Hey guys, good morning, good afternoon. I'm waiting for these notes to load. We are in the next section of notes with metamorphic rocks. I believe it's on page 4. So group A, this is for you guys or for kids that are at home. And yesterday was igneous rocks. So if you were not here yesterday, there was a puzzle that went with that. You should have taken care of that yesterday, I hope. So on to metamorphic rocks. So up there in that picture, first of all, just some clarification. Those are two different types of metamorphic rocks. One's called gneiss, that G is a silent G, and then schist. Kind of a maybe a little naughty, but funny joke. Okay, so metamorphic rocks. This is a type of rock that is created from previously existing rock, and it is metamorphosed, which means to change. It's changed by heat, pressure, or a combination of both. So what happens is you take a rock that's a pre-existing rock and you change it by either increasing the temperature, increasing the pressure, maybe both of those. And then the third, which can also happen, is either the addition or loss of fluids. And again, we call that metamorphism, to change. If you think about that, that applies to animals too that go through a metamorphism. It's a change that happens. There's a couple of good, quick little videos with some good visualizations to help understand these processes.
Metamorphic rocks form when heat, pressure, and usually fluids change or morph the original or parent rock into a completely new rock. Igneous and sedimentary rocks become metamorphic rocks in this process. Metamorphic rocks can be metamorphosed as well. As we descend deep into the earth, both heat and pressure rise. On average, temperature increases 3.6 degrees Celsius per 100 meters of depth. Increases in pressure may also be directional, occurring, for example, from the stresses caused by plates, colliding in the process of mountain building, or sliding past each other, such as the shearing stresses at the San Andreas Fault in California, or the Dead Sea Fault in the Middle East.
All right, so metamorphism means to change. I talked a little bit about how that can happen. All right, so we're going to go through each of these variables. So the first variable is temperature. So if we increase temperature, the deeper we go in the earth, the hotter it is. Some of the effects of increasing temperature are the following. It could cause a change in the mineral composition. We talked about that yesterday with igneous rocks. Different minerals are formed at different temperatures and different pressures. So as you change the temperature, it would change the mineral composition. The heat can also cause chemical reactions to speed up, which make the atoms move a little bit differently, which would cause a new rock. Sometimes, and most often, it would cause a new rock that is going to be denser because it's become more compacted. If you change the arrangement of the minerals or change the arrangement of how those atoms are aligned, it would create a new mineral. And then it can also drive fluids out of the rock. So a lot of rocks, I know you don't see it, you don't know it's there, but there's water, there's oxygen, there's carbon dioxide in a lot of rocks. And if you increase the pressure or the temperature, you can force some of those fluids, which are in the gas form, out. Now, one thing to remember, that the rock remains solid through this process. Okay, remember, what is an igneous rock? An igneous rock is a rock that forms from material that was once molten. So if we add too much heat and the rock melts, we're not going through metamorphism anymore. We've now gone back to creating a new igneous rock. If pressure is increased, there's a few things that happen. It's a really good picture over on the right that shows this. You can see on the left picture over here that before metamorphism, the arrangement of the crystals or the atoms are kind of all over the place, and that's shown in this rock right here. If we increase pressure from the left and the right, as seen in this picture on the right, so we're pushing from the right, we're pushing from the left, it sort of forces those minerals to align themselves, and you can see that banding that happens in this rock right here. So it's a change in the shape and the arrangement of the mineral crystals, which would change the identity of the rock, creating a metamorphic rock. If a rock becomes more compact because pressure is applied in all directions, again, it changes the mineral alignment, the mineral composition. The texture can change in cases, but also keep the mineral composition the same. So that can happen as well. Keep that in mind. Typically, the new rock is going to be denser and harder than the original rock, just like with a change in temperature. It's typically going to become denser. And if the pressure isn't applied equally in all directions, so like let's say there's more pressure on the left versus the right, you may get some layers that show up, and those are called foliations. We'll look at that in a few minutes. So metamorphic rocks are classified, and their name is based on their texture and their composition, just like igneous rocks, those two things. It's going to look a little different because they use some different terms here, but it's going to be sort of the same classifying process based on texture and composition. Composition means what it's made of. So remember that there's two major categories of texture that we use, and the two words you need to know are foliated, which means it has these bands, you can see lines in it, or non-foliated. So this over here, you really couldn't tell what direction the pressure was applied. Over here, we can tell pressure was applied from the top and the bottom, creating these bands that run through. This video also explains this a little bit.
Metamorphic rocks are either foliated or non-foliated. Foliated rocks like slate and schist are metamorphic rocks that have bands of minerals that have been formed when pressure is greater in one direction than another. This pressure causes the minerals in the rock to reorient, so they form mineral layers perpendicular to the direction of pressure. By contrast, non-foliated rocks don't show this type of mineral banding. Quartzite and marble are two examples.
All right, so good visualization of the banding that takes place for foliated rocks and how it's not existent with the non-foliated. So foliated metamorphic rocks, there are within foliated some subcategories that you'll need to know. So metamorphic rocks that have a foliated texture have their mineral grains that are aligned in nearly parallel planes or bands. So you can kind of see over here, there's bands that are parallel to each other. These will appear as layers. And again, this is not to be confused with layers that we see in sedimentary rocks, which we'll talk about on Monday next week. It results from pressure being greater in one direction than another. So in this case, pressure was applied from the left and the right, not from the top and the bottom. Now, the three subcategories are called slaty cleavage, schistosity, and gneiss-ocity. Okay, so that G, we don't say that G in gneiss-ocity. It's like the word nice. So cleavage is a property that we find in certain minerals that causes rocks to break along distinct planes. So like you could see right here, these are the planes right here, these like layers that you can see. And if you were to kind of take something to chisel that away, this rock would break along those planes. So we call those cleavage planes, and it can be in just one direction, or we can find them in several directions. So slaty cleavage is the texture of slate. Slate is a type of rock that can split into thin, flat layers along those parallel planes. Schistosity is named after a type of rock, schist. It's a texture of schist that has really strong foliations or bands of coarse-grained platy minerals such as mica. So we would take this rock right here, if we were to apply a lot of pressure to this rock, which happened over here. So this schist turned into mica by applying a lot of pressure. And you can tell by looking at it that there would have been pressure from the top and pressure from the bottom. And it creates these really, it's almost a flaky type of rock, and you can break it along those planes. Gneiss-ocity is another type of foliation that we find, and this has to do with the rock gneiss itself. And what we see are alternating bands of light and dark materials. And if I were to break this rock, it wouldn't break along those planes like the other two would. It would break in a more irregular type of pattern. So non-foliated rocks, the ones that don't have the bands, these are composed of mineral grains that are not aligned to any plane. They don't have a pattern to them. We don't see those bands. So typically with these rocks, the mineral grains are all about the same size. They have a granular appearance. If you've ever seen a sugar cube, that has a granular appearance. So it's sort of rough and bumpy. And it's usually composed of one material. Marble's a very common one. And then others are composed of microscopic crystals that are of different minerals. Hornfels is a very common one. And we typically will call, because it's so common, we typically call the non-foliated texture a Hornfels texture. So these are all examples of non-foliated rocks. You can see that there are no bands, there are no like lines running parallel to each other. This is marble over here. We have quartzite on the right, and then a couple more down at the bottom. This is a different type of quartzite. Obviously, it's got a little bit darker color to it, and then this is marble here as well. So what causes that non-foliated appearance? If there's not pressure squeezing it into bands, it must be, it could be a unique type of pressure that's being, or it could just be heat. So one thing that could happen is if you have pressure that's applied in all 4 directions with equal amount, you wouldn't get any bands. So it'd be pushing from the top, the bottom, the left, and the right with equal pressure. But more common, we find non-foliated with an increase in temperature and no pressure goes along with it. If there's lack of directional pressure, that means the minerals are not aligned into those bands. So over here are showing you a parent rock that goes through metamorphism and turns into something else. So marble is usually the result of limestone. So limestone is not a metamorphic rock. It goes through some metamorphism and it becomes marble. Another is sandstone, a type of sedimentary rock. And as that undergoes metamorphism, it becomes something we call quartzite. So metamorphism, as far as heat goes, can happen in a couple of different ways, heat and pressure. And we call it contact or regional metamorphism, and they're named as they are. So contact means it's the result of a pre-existing rock coming in contact with magma, possibly underground. Regional means it occurs over a very large region and typically is a result of pressure, not heat. So this does a little explaining of that concept.
Of many different ways metamorphic rocks can form, 2 major types are contact and regional metamorphism. Contact metamorphism occurs when there is an intrusion of magma into existing rock. The resulting increase in temperature and pressure causes the surrounding rock to change. Marble is created in this way out of limestone. Regional metamorphism occurs on a much larger scale over wider areas of continental crust, as large-scale forces of plate tectonics bend and break the rocks. The tremendous pressure these rocks are subjected to is typically associated with mountain building.
All right, so that was a good visualization of metamorphism happening either through direct contact or through regional pressure. So we'll talk a little bit about each of these real quick. So contact metamorphism, this is where a pre-existing rock comes in contact with magma underground. The contact that would cause the rock to melt, now remember that's going to be an igneous rock, but the part of the rock that changes just from the heat that's nearby, this is what we're talking about right here. So as magma forces its way from the mantle toward the crust, this bubble, if you will, or this area of magma is called an intrusion. We have a picture that'll show us it in a minute here. The surrounding rock is called country rock. No, not like the music country rock, but we just call it country rock. It's like the pre-existing rock that was there. So as the magma works its way through or near the country rock, it comes in contact with that country rock comes in contact with the hot magma, and it's enough to cause metamorphism. And the portion of the country rock that actually becomes a metamorphic rock, the rock that actually goes through a change, is referred to as an aureole, sort of like the bird, the oriole. So here's a picture of what's happening. Here is your intrusion of magma, and the country rock is identified here as like this yellow area right here. So this is the pre-existing rock. And then in this area right here, where we have the new rock, this is the contact metamorphism. So this is the rock that did exist, the country rock, and as it comes in contact with the magma, there's some fluids that are lost, but there's the heat contact that causes the rock to change into a metamorphic rock. So those are words you'll want to know. You will want to know, going back to that, you'll want to know what the intrusion is. You will need to know that the country rock is the pre-existing rock. And you'll need to know that the new rock that's formed, this like light pink area, the new metamorphic rock is called an aureole. So the aureole itself, here's another picture showing this. The size of that new rock, that new metamorphic rock or the aureole, is going to depend on a couple of factors. Number one, it's going to be determined by the size and the temperature of the intrusion. So here's our intrusion. Obviously, a bigger intrusion would create a bigger aureole. The amount of fluids that are in that magma will also determine this. And when I say fluids, remember fluids can be a liquid or a gas. So this could be gases that are in there as well. And then what is the country rock? So here is your country rock. All of this was country rock, the pre-existing rock. They call it the surrounding rock here. And then here's our new metamorphic rock. This is the aureole. So those three factors will determine how big this new rock will be. A bigger or hotter intrusion obviously results in a bigger and wider aureole. And then the portion of the aureole that's closest to the intrusion will usually have a higher degree of metamorphism. So like right along here, because there is that direct contact. And then the further you get away from it, less metamorphism. So regional, again, this is the one where it's not in contact. This is over a very large area in the Earth's crust, and it's usually a result of tectonic plate movements. So this is a much larger scale change that's happening than contact. And it typically is going to occur at your convergent boundaries where you have pressure on each side, and the differing amounts of pressure on each side typically result in a foliated metamorphic rock. So there's uneven pressure that causes that on each side of the convergent boundary. So here shows regional metamorphism, so you can kind of see what's happening. Over here are a couple of things. Number one, let's take a look at the temperature. You can see the deeper you go, the greater the temperature. And also with that pressure between these two plates converging along this boundary right here, you also are going to get some heat that's derived from that intense pressure. So this is sort of the one that's subducting a bit. Here's the overriding. This is two pieces of continental crust. And right here are different types of metamorphic rock. So depending on the amount of pressure, you might see different degrees of metamorphism happening and different rocks that will result as there being unequal distribution of heat and pressure. So what this does, usually this results in the burial of lots of rocks, typically at a subduction zone, like I said. It can bring previously buried or new metamorphic rocks up to the surface. Typically this is going to be found in the mountain building process. And then it occurs over areas that are very, very, very large, typically continental crust that's composed of a lot of already existing regional metamorphic rocks. And that is it, my friends.